Hello, everybody. We're going to be talking about solutions and concentration, taking a mathematical look at these solutions that we've been talking about. And this is practically a very important skill. In my first lab job, I did a lot of work involving creating solutions and dilutions and whatnot, and we'll see how to take a quantitative approach to that right now. So recall a few things about strong electrolytes, weak electrolytes, and non-electrolytes. Strong electrolytes are good conductors. They dissociate completely in aqueous solution. So we use those full-headed arrows to show that when these things go, they go all out. And our examples for these are strong acids, strong bases, and salts. Then we have our weak electrolytes. They create a marginal amount of ions in aqueous solution. Our big examples of those are weak acids and weak bases, specifically carboxylic acids and amines, respectively. And then finally, we have our non-electrolytes. They stay completely covalently bonded together. They're not going to be forming ions in aqueous solutions, so they don't conduct electricity. Okay, we've also looked at a number of different ways of measuring concentrations throughout the course. We've looked at mass fraction, where you have the mass of a solute divided by the total mass of a solution. We have mole fraction, where you're looking at the relative number of moles of something solution. We have parts per million for dilute things. We have mass fraction that we've looked at. Today, the focus is going to be mostly on this entity called molarity, which we express with a capital M. And molarity is defined as the moles of the solute divided by the total liters of solution. So a few relationships to show here. Molarity is equal to moles per liter. Classic. We can also rearrange this to get another powerful equation. The number of moles of a given solute are equal to the molarity of that solute times the liters of solution. So these are going to be very useful moving forward. With that said, let's move forward. And something with solutions and dilutions, it takes a little bit of practice to master, but once you get it down, you get it down. So actually, most of our slides today are going to feature these interactive question experiences, where there'll be a number of answers, and you are encouraged to pause the video and take the old college try at these questions. So I'm going to kind of freeze in place for about 5 seconds, give you a chance to pause and do the question and see how you did. All right, you did it. Let's go through this problem. So we're trying to find here the amount of grams of sodium chloride that we would need to make a 5 molar solution with 500 milliliters of our solution. So one of the big things with solution, dilution problems is oftentimes you'll see there's a large number of numbers. So kind of designing a plan on how you're going to get to your answer is the key to success in these. And mathematically, it's not super taxing. It's just figuring out what's going on and what units go where. So first, let's recall that molarity is equal to moles of solute over liters of solution. Do we know any of these things so far? Well, yeah, we know the molarity. We want it to be 5 molar. And we know the liters of solution. 500 milliliters is equal to 0.5 liters. So we can rearrange, get this moles of solute is equal to molarity times liters of solution, like we discussed on the previous slide. So take that 500 milliliters, there are 1,000 milliliters in 1 liter, and we get 0.5 liters. Okay, so our moles of solute are going to be equal to 5 molar, that's the concentration that we're looking for, times the 0.5 liters that we're trying to make, equals 2.5 moles of sodium chloride. If we know moles, can we find grams? Yeah, you bet we can. So sodium chloride clocks in at a cool 58.44 grams per mole. And we end up getting 146.1 grams. And so with our 2 degrees of precision here, we end up getting, it's about 150 grams, okay? So, and this is actually a very, very useful thing if you do work in a lab at some point, because making solutions, especially like buffer solutions to run experiments in, is important, and you need to have the right ratio of these various acids and bases that go in. Okay, now we're looking at the molarity of pure water. So you have a glass of water, we want to know what the concentration of water is. Believe it or not, now you can find the concentration of water, and that's exactly what we're going to do in this interactive question experience right now. All right, let's see. So remember, molarity is equal to moles of solute over liters of solution. And we're given the density here. It doesn't matter how much of this water we're looking at, because the concentration of water, if we're looking at a glass of water versus a pool of water, is going to be the same. So I'm arbitrarily going to assume 1,000 grams. Any mass would work here, but 1,000 grams is going to be easiest. So we take those 1,000 grams. For every 1 gram, there's 1 milliliter, which gives us 1,000 milliliters. Okay, great. So we know the number of liters, that's 1. All right, well, since we have the number of liters, which is 1, in order to get the molarity now, what's the missing piece? So we have liters of solution at this point, check. We're trying to find the molarity. We need to find the moles of solute. And remember, if we know the grams, we can find the moles. So we have 1,000 grams of water. Water is 18 grams per mole. And so we end up getting 55.66 moles of H2O. Cool. Now that we know the number of moles of H2O, we can just divide that by the number of liters, which is, well, 1. And so we end up getting 55.56 moles divided by 1 liter, which is 55.56 molar. So if you're curious, the next time you have a glass of pure water, the concentration of that water, 55.56 molar. This next question is about acetic acid. That's what gives vinegar its punchy taste. Turns out a lot of vinegars are about 5% or so acetic acid by mass. So we're given a density here of vinegar, and we're trying to find the molarity of acetic acid in a 5% acetic acid by mass solution. Okay, so there's no answer choices here. Or are there? Yes, we have another interactive solutions question. So go for it now. Okay. In order to make our lives easier, we're going to choose a nice round number. Again, it doesn't matter how much we choose to work with. We could choose, in fact, we could start with grams instead. We can start with volume. We could start with 1 billion liters. Let's just start with 1 liter. Make a nice round number. So 1,000 milliliters. There's 1.01 grams for every 1 milliliter of solution, which gives us 1,010 grams of solution. And we know that this solution is 5% acetic acid. So we'll multiply that number by 0.05 because 5% of it is the CH.COOH, and we'll get 50.5 grams of acetic acid. Okay, so now what are we trying to find here? We're trying to find molarity, moles per liter. We already know liters because we're arbitrarily choosing 1. That's the reason why we chose 1. We need to convert this into moles. There are 60 grams of CH.COOH in 1 mole, and this ends up being 0.84 moles of acetic acid. So because we chose a nice round number to begin with, molarity is moles over liters, and we end up getting 0.84 molar CH.COOH. Okay, so now let's look at electrolytes. When we're looking at strong electrolytes, we need to remember that the substance will dissolve completely into its respective ions. So specifically, let's look at calcium chloride here. For every 1 calcium chloride we have, when it goes into water, it'll dissociate into how many ions? It'll dissociate into 1 calcium 2+, and the 2 chlorides. So for every 1 calcium chloride, we end up getting 3 ions. And we could find that if we had, say, 1 molar of calcium chloride, we could find the total molarity of ions by doing, it would split into 1 mole of calcium 2+ and 2 molar of chloride, because for every 1 calcium chloride, we get 2 chlorides. So that would mean that a 1 molar solution of calcium chloride is actually 3 molar in total ions. This is notable in something called colligative properties. We don't discuss it that much in Chem 110, but it's what makes ice melt work. So ice melt is actually calcium chloride. Turns out the more concentrated a salt is in water, the more the freezing point goes down. And so by putting it on ice, you greatly lower the freezing point and hopefully to a point where it'll turn into a liquid. Okay, so now we have this question. Which of the following aqueous solutions contains the largest concentration of nitrate, NO3- ions? Well, guess what? It's another interactive question experience. So we're already given the concentration here, and we're looking for concentration. It doesn't matter if we're looking at 10 milliliters versus 100 milliliters, et cetera. It's all about the concentration. So for the cobalt nitrate, we have 0.5 molar cobalt nitrate. for every 1 cobalt nitrate, we get 2 nitrates. So the actual concentration of nitrate would be 1 molar. And we go down to this ammonium nitrate. It is 1 molar, but for every 1 molar, for every 1 ammonium nitrate, we only get 1 nitrate. So it's still just 1 molar. Okay, so far we have a tie. The last one, we have aluminum nitrate. For every 1 aluminum nitrate, we actually get 3 nitrates because aluminum has a 3+ charge, so we need the 3 nitrates to counterbalance it. So we end up getting 1.2 molar nitrate. Ding, 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 we have our winner. So now we're going to talk about transfer versus dilution. These are 2 key phrases that are used when talking about preparing solutions, and they're very different. So transfer is when you take something from one vessel and pour it into another. If you pour something from one vessel into another, is the concentration of that liquid changing? Well, no, the concentration is going to remain consistent. However, the volume and the number of moles do change as you pour more out from your stock solution. The stock solution goes down, whatever you're transferring into goes up. Same concentration, but you're changing the number of moles and the volume. On the flip side, we can also do something called a dilution, where we add water to something. When we add water, the number of moles of the solute remains consistent. So if we're looking at molarity, molarity is moles per liter, the mole stays consistent, but we have more liters of solution. So that means that our concentration will actually go down. So the volume and concentration are going to change. Which brings us to a segment. Some live chemistry action, dilution and transfer addition. Let's take a look and try to visualize these concepts in action. And action. I have here 2 beakers. One of them has water with red food coloring. One of them has nothing. If I transfer from one to the other, so I'll notice here, it's relatively even, that in terms of the intensity of the dye, pouring this out, it remains consistent between these 2 different glasses. This is an example of transfer. When I transfer, the concentration doesn't change. Now, however, I happen to have another glass full of just water. If I put this water into this glass, notice what happens to the intensity of the dye. This is not recording nearly as well as I thought it would. If, on the other hand, I take this vessel and I pour water into it, you can see that the intensity of the color is getting much, much, much fainter. This is an example of dilution. Another example that I like to use is orange juice. So with orange juice, it doesn't matter if so here's my stock solution of orange juice. I'm going to transfer some. So here we have a transfer into this glass. Okay, so now I've got a glass of orange juice and I've got this stock solution of orange juice. Doesn't matter if I take a sip from the glass or a sip from the initial vessel, it still has the same concentration of orangey goodness, the same concentration of citric acid and sugars, etc. If, however, for some reason, I were to pour water into my orange juice, now it's not nearly as concentrated with its orangey goodness anymore. That was a dilution. Now it has the same number of calories as my glass of orange juice had. It's just now it's much more dilute, much less concentrated. All right, let's do some more problems. So here we have a 10 milliliter solution containing 2.25 molar sodium phosphate. It's diluted to 40 milliliters. We want to know how many moles of Na+ ions are in 20 milliliters of the dilute solution. So many things going on here. Pictures can be really useful. Little diagrams for figuring out what steps things take place in, and then the calculations themselves fall into place. So, oh, all right, you tell me. All right. So let's see. We're starting off with a 2.25 molar solution of sodium phosphate. And remember, molarity is moles per liter. The other important relationship here, just manipulating that one, is moles are equal to molarity times liters. So we're going to use these equations to solve this problem. First things first, how many moles of sodium phosphate are there in the initial stock solution? So it's 2.25 molar, and we have 10 milliliters, which is 0.01 liters. That'll tell us the moles of sodium phosphate, 0.0225 moles of sodium phosphate. Okay, now notice, we're looking actually for the moles of sodium in this problem, so we'll need to keep that in mind. 0.0025 mole of sodium phosphate. For every 1 sodium phosphate, we have 3 sodiums, which gives us 0.0675 moles of sodium. Okay, so now we know that. Now what we're going to do is, that's the number of moles in the solution. Our dilute solution has 0.0675 moles of sodium as well, because when we dilute it, do we change the moles of sodium or anything in there? No, we're just adding in more water. So our concentrated solution was 0.0675, or had 0.0675 mole of sodium. Our dilute solution will have the same. So now we can find the concentration of that dilute solution. It's 0.0675 mole of sodium divided by 0.040 liters, which gives us 1.69 molar of sodium plus. So now we have the concentration of that dilute solution. But is that what we're looking for, the concentration? No, we want to know how many moles there are in 20 milliliters of it. So we're taking the solution, we're diluting it, and then we're transferring out a little bit. Well, we know that when we transfer, the concentration is going to be the same. So that little beaker there, that represents our transfer of the dilute solution. All we have to do now is take the molarity, which is 1.69 molar, multiply it by the volume, the 0.02 liters, and we'll end up getting 0.034 mole of sodium. So there were a lot of different conversions here. Basically, though, it was the roadmap that was the most important part. Once you know how to set these things up, the rest of it falls into place. Okay, so here we have yet another question. And look, all this information, 20 milliliter sample of magnesium nitrate was diluted with water to 7 milliliters. A 15 milliliter sample, the dilute solution contained 1.130 molar of nitrate. What was the concentration of magnesium nitrate in the original undilute solution? Whew, a lot of information here. Okay, again, as long as we map it out, we'll be just fine. You might have seen that coming. It's an interactive question experience. Let's get to it. Okay, there are possible answers. Let's see if we got the right answer. So our dilute solution was 0.13 molar nitrate. Okay, that means that it doesn't matter if we're looking at the transfer from the dilute solution or the dilute solution itself, it's the same concentration. So even though we transferred 15 milliliters of that dilute solution, if it had 0.13 molar of nitrate, that means that the solution, the dilute solution, had 0.13 molar of nitrate. So now that we know that, the moles of nitrate in the solution are going to be equal to the 0.130 molar times the 0.07 liters that were in that dilute solution, which gives us 0.0091 mole of nitrate. Okay, now how does that number of moles of nitrate relate to the number of moles of nitrate in the original non-dilute solution? When we pour in water, does it change the moles of nitrate? No. So that means that our dilute solution had 0.0091 moles of nitrate. Our concentrated solution also had 0.0091 moles of nitrate. Okay, now that we know the number of moles, we can convert that into moles of magnesium nitrate. So for every 1 magnesium nitrate, there are 2 moles of nitrate, which ends up giving us 0.00455 moles of magnesium nitrate. And then finally, what are we looking for here? Well, we're looking for the original concentration. Concentration is moles per liter. So we know the number of moles now. We just have to divide that by the original volume, which is 0.02 liters, which gives us 0.228 molar magnesium nitrate. Cool. Again, a lot of things going on here, but mathematically not super taxing. It's the strategy that's really important. Now, it turns out that when you do a dilution, there's a little bit of a shortcut, actually a very useful rule that you can utilize, especially in a lab. So given that the number of moles is equal to molarity times volume, M times V, when we do a transfer, we don't change the number of moles. So if you have initial molarity and initial volume, that gives you the moles. If you dilute it, then the number of moles remains consistent. You will, however, have a new molarity and a new volume. So now, because N is constant, we can actually set these equal to each other. And we get the dilution equation. M1V1 equals M2V2. This will work if you're doing a dilution. So, and I should warn you, it is sometimes overused, but if you're doing a dilution, it works really, really well. So that previous problem we did, we knew the initial amount, we knew the initial concentration, or we knew the final concentration after we did the dilution was 0.065 molar magnesium nitrate. So what we could do here is we could take M1V1 and set it equal to M2V2. So our dilute solution was 0.065 molar, and we had 70 milliliters of it. We know that we started with 20 milliliters, so that's our V1. So we can divide both sides by 20 milliliters and get 0.2275 molar, which is the same answer that we got before, 0.228. So this is a useful shortcut whenever you're doing a dilution. It works really, really well. We could also go through and find the number of moles and do what we did on the previous slide. But if you have dilution, this works nicely. Okay, and now let's do this problem. We've got 50 milliliters of 0.436 molar ammonium nitrate. We're adding it to 200 milliliters of 0.16 molar barium nitrate. What's the final nitrate concentration? The resulting solution. We're assuming the volume is additive. You betcha, we've got another interactive question experience. Let's see how you did. Okay, so we're pouring two things together. Each solution has its own amount of moles of nitrate. So we're going to find the total moles of nitrate being poured together into the same flask here. So from the first solution, it was 0.436 molar, and we had 50 milliliters, 0.05 liters, which gives us 0.0218 moles of nitrate. That was the amount from the first solution. But wait, we had a second solution. So we'll take the 0.16 molar. We'll multiply it by the 0.2 liters. And remember, for every one barium nitrate, there's actually two nitrates. So we're going to multiply this value by 2 and get 0.064 moles of nitrate. So when we pour these together, the number of moles is additive. All we have to do to find the total moles of nitrate is add the amount of nitrate from solution 1 and the amount from solution 2, and we get 0.0858 moles of nitrate. Okay, we know the moles of nitrate. What is it that we're actually trying to find? The concentration in the solution. So if we pour the two solutions together, the final volume is going to be equal to the sum of the two different volumes. So all we have to do to find the final volume is add up. We have 0.25 liters total. We had 50 milliliters, 0.05 liters from the first solution, and 0.2 liters from the second, which gives us 0.343 molar of nitrate. And that concludes our discussion on solutions, dilutions, and concentration. So again, at first, this can be a little bit difficult, but the more you practice with it, the easier it gets. And eventually, once you do enough practice with it, you will master it. So keep up the great work and have an awesome day.